Welcome everybody. We're on the top of the hours. I will start with some basic Zoom usage. So feel free to use the chat to talk amongst yourselves. I think I need to unmute you if you want to ask questions. So please raise your hand, and I'll be glad to have your questions during the talk. You can also use the question and answer feature. So please do that if you prefer. And I will try to answer the questions during the presentation or after it, should there be a need for a long discussion about those. So welcome everybody to the OpenCL for Layers for OpenCL tutorial. So I'm Brice Videau, at work at Argonne's National Laboratory, where I'm doing a lot of heterogeneous programming and system work. So I'm using both of these hats today for this Layer for OpenCL tutorial. So the session is split into two. There will be a presentation plus questions that should last us the first hour, more or less. Then we'll have a break, and I will dive into an online presentation of how layers work. And I will be glad to take more questions after the demonstration. Okay, so let's get started on the slides. That's the wrong focus. So what is the context of layers first? And what are they? So I will be defining that in the first part of the presentation. So the first big context is that applications have become increasingly complex. The environment is more complex. The hardware is increasingly heterogeneous. We have GPUs from several different vendors. We have several abstractions. And so the application have adapted to the different hardware by abstracting away the differences, creating new layers of abstraction between programmers and the hardware. And it is sometimes difficult to understand how this application behaves and to debug this, because you need to traverse 1, 2, 3, 4, sometimes more layers of software to understand what bugs you're facing. Applications are built on top of libraries. And one concept that is important here is that you can use libraries as a window into an application. The reason being, libraries present what we call an application programming interface, API in short, and that these APIs are programming models. They have a self-contained, coherent design that allows them to, and their usage especially, to be validated. So the idea is that however complex the programming model of the libraries you're using, usually if you look at different calls, you should be able to understand what is going on and what is the user's intent. So the question is, okay, we know we should be able to validate the library's usage. What is the information we need to validate this usage? And what is the cost of acquiring this knowledge? So the first, and I already alluded to it, is we need to know what function of the library is called and when. The next level of granularity is, but what parameters did the user use when it called the function? And what did the function return? The next step is, okay, we have pointers, we have integers, we have floating point values. What is the meaning of those parameters? Is this pointer an object? Is this an object I've already seen previously? Is this integer a size? And then it refers to the size of what? And so on. And the next level, and it's quite entangled with the previous one, is what is the state of the programming model when you enter the API? And what is the state of the programming model when you exit the API? So the idea is, and I will use a simple malloc-free example, is that if you allocate memory, for instance, you get back a pointer. If you have the arguments of the malloc memory allocation, you know that the memory you just allocated is a certain size. So you know that on your system, there exists a memory allocation and you have its size. So you can check when you are releasing the memory that the pointer does exist. But you can also check when a memory location is accessed by another function, if it's something you've already allocated, or if it's in a range you've already allocated on that. And you need to conserve the state of that if you want to, meaning that you will have a hash table, for instance, where you have the pointers that malloc return and the size that is associated to it. And when you free, you will move this allocation, remove it from the hash table, and maybe move it to a list to store the fact that you used to have this pointer available, but it's already been released once at least. So the big question is, all of this is very nice, but can we do this outside of the application? And the second, and maybe even more interesting question is, can we, on the fly, modify the behavior of the programming model we are using? And we will be trying to answer this question during the presentation, and especially for OpenCL. So the idea of doing that outside of the application is to use library interception. So for a shared library, interception, or it's also called interposition, is the strategy that is usually used. So the idea is that you don't want to manually instrument your application, or even automatically instrument your application by modifying the application itself. So the idea is, if you're using a shared library, you can use another shared library to replace it by presenting the same symbols, or at least part of its symbols. That would be used preferably to the real library symbols, which are usually functions, but can also be global variables and this kind of things. So you create a shared library that implements the function you want to trace. And underneath, this shared library will use the real library to not have to redo all the work that the library is doing. And depending on the system, it may be a bit different, but the idea is always the same. You use the dynamic linking of libraries to load this library before the real library. So the small graph below presents exactly this. We want to instrument malloc and free. So we have an application, and we have a preloaded library the application will use a malloc and free inside the library, and the library will forward the call to the real library which implements malloc, free, and str, and other functions. And the function that our preloaded library does not implement will be implemented by the real library. So I also wanted to show this graph because there is a little trick here, is that there are other functions in the libraries that implements that allocates memory. So str_dup is one of those. So one needs to be careful that some function that looks rather innocent may have a big impact on the API and on the state of the programming model. So if you use str_dup, it copies a string, but it also allocates the memory to do the copy. So you should intercept str_dup if you want to be sure to catch all the memory allocations. And in the end, you need to use free on what was returned by str_dup. And so if you see a free that is on an unknown pointer, it may not be an error from the user. It may just be that your preloaded library is not covering the API at 100% on the memory allocation front. So that is one of the hiccups, is that you need to know your APIs very well. So more related to OpenCL, an example famous in the community of this strategy of the preloaded library, and its complete coverage of OpenCL, is Intercept Layer for OpenCL Applications. So it allows you, using interception strategy, to trace every API call in the OpenCL standard, and some extension also. So that's for library interception. What are the limitations of library interception? And why do we want to use maybe something else to design layers for OpenCL? So the limitations I can see here is that first, the interception will depend on platform-specific functionalities. How do you load a library? How do you preload the library? How library destruction is handled, and construction, and so on. Also, if you want to have several interception libraries, not only one, it can prove quite difficult depending on how you configure them. Because you could configure them via environment variables, saying, oh, this is the library you should load. Or you should trust the dynamic linker to give the libraries in order. And you should use functionalities that say, give me the next implementation of the function that is available. All of this is quite tricky. And the other reason is that you may need to write quite a lot of boilerplate code to express those abstractions if you want to get started. So can we also alleviate these issues for OpenCL? So the idea here is to say, what if this interception could be provided as a plugin by OpenCL? And there are examples of this already. So not something that I invented, of course. You have layers for Vulkan. You have concepts similar for MPI. For in the new OpenMP standards, you have a tracing API for OpenMP, and so on. The benefits are clear. We are factoring platform-specific concerns. We are factoring boilerplate code. There is a clear protocol implemented to understand how to deal with several libraries, several plugins. And we standardize the API for the development of those layers. So what I'm going to present in this tutorial is the design and the implementation of the layers for OpenCL and how to develop a layer for OpenCL. So, the first part is we need to look and dive a bit into how the OpenCL installable client driver, which is called ICD loader, work. So installable client driver is ICD. So the OpenCL ICD loader, how does it work right now? And how will it work? Does it work with the layer support enabled? So what is the OpenCL ICD loader? The OpenCL ICD loader is a library that is installed on the system, usually by vendor drivers. And the idea of this client driver loader is to be able to load drivers from different vendors using the same interface. So it takes care of loading and verifying that the drivers are correct. So they implement a known extension, which is SYCLcon ICD, which says, I am a driver that can be loaded by the OpenCL ICD loader. And it has a bit of options to allow the users to load alternate drivers if they want, and to change how the system loads those drivers, or maybe change the ordering of those and so on. So in this talk, I will be working exclusively with the official OpenCL loader from Khronos. So the name of the library is libopencl, .so or .dlib if on Mac. On Windows, it's named OpenCL.dll. So if you see an OpenCL.dll, it's a Khronos loader, most probably. And it's not the real OpenCL driver. The real OpenCL driver was installed by the vendors or by the distributions on Linux. So how does this OpenCL ICD loader work, and what is the workflow of a call? So the idea is that the loader will act as a router, so a demultiplexer, and it directs the call to the right vendor driver. So let's take a simple example of an application, and you have two potential drivers. The idea is that you are able in OpenCL to create contexts that use devices from the different vendors. And in each of those contexts, so each context only uses devices from one vendor. When you use this context, you create objects, queues, memory allocations. And the idea is that the OpenCL ICD loader is able to, when you do an operation on a device or on a queue, to redirect this call to the correct driver in order for the OpenCL model to work and for your drivers to coexist. So you can use an AMD and an Intel GPUs at the same time, for instance, using OpenCL. It's entirely possible. There are limitations, but you can do it in the same application, thanks to the ICD loader. How does that work? So the idea is that each object in OpenCL, in order for OpenCL to be able to use it, to use several implementations simultaneously, is defined as a structure. And the first member of the structure here is a pointer to a table where you have a function pointer to the functions implemented by the vendor. So the idea is that all the OpenCL functions from the standard that are supported by a driver are gathered in a table that is the first element of a device or a platform or a memory object and so on. So the object carry with themselves the reference to the functions that needs to be called with these objects. And that's how the dispatching is done. So if you have to write an OpenCL loader function, so for instance, what is the job of the OpenCL ICD loader? It's quite simple. You need to check that the object is not null, because if the object is null, you cannot use it to read the table of the functions. And then you need to call the correct function in the dispatch table. So this code here is actually the way it used to work before there were layers, exactly. So I took the example of the CL get device info function, which is a function that gives you the information about a specific device. So it takes 5 parameters, which one is the name of the parameter you want to query, and the size of the pointer you are giving the runtime to get back this parameter value, and a pointer so that you can query the size of this parameter value should you need to. And the implementation is as simple as what I described. If the device pointer is null, then you return CL invalid device. Else, you go inside the dispatch table, you get the CL get device info function pointer, and you call the function. And you've made your dispatch. So the OpenCL ICD loader implementation for most of the function is really pretty simple and easy to understand. So if we want layers, how would that work from a workflow perspective? The idea is that the ICD loader, rather than calling right away the function or validating the object first, will redirect the call to the active layers. And then only when all the layers have been called, should we dispatch the call to the correct driver. So the ICD loader would still be doing the same job of dispatching, but it will be having an additional task, which is forwarding the call to the layers that are active. And the idea is that a layer may not need to implement all the functions. So here we have a small example where we have several layers. And so some layers could be skipped. Like, for instance, here, the first layer. The first layer has not implemented function 1. And so the function 1 is directed to the next layer which implements it. Function 2 is implemented by layer 1 and layer n. So there may be additional interception in between, but the idea is function 2 on the first layer would be executed and then forwarded to the next layer in the chain. And then we are back into the loader to do the dispatch in the drivers. So how can we implement this scheme? And what constraints do we want to have on this scheme? So the constraints we fixed ourselves is that we don't want undue overhead when the layers are not used. We don't want this to be costly when you're not using your layers. And we don't want it to be costly when you're using layers, but there is an inherent cost associated with the layering process. We cannot avoid that. We want to be able to chain layers and as many as we want. And the layers must be simple and easy to write and understand. So what is the idea here from the layer side? The idea is that the layer will be given a complete dispatch table they can use to call OpenCL functions. Even if they don't need it, that's not a problem, but they will be able to call any OpenCL function. But they will need to do this through the table. They must not call an OpenCL function through the driver, else you could have a loop. And the layer, in return, will give back to the loader a dispatch table of the function they implement. It may be incomplete. From the loader side, the layer will maintain a list, the loader will maintain a list of the loaded layers. Each new layer is added to the front of the list. Sorry about that. Each layer is added to the front of the list. And the idea is that each layer is passed the previous layer dispatch table as a target. And if you're the last layer, the first one to be added, you're pointing to the loader dispatch table first. So if the tables are incomplete, you complete them with their target. So in practice, let's take an example. We have the loader that has already loaded dispatch table n-1. And we want to load the next dispatch table. So as you can see here, we send the layer the previous dispatch table, and the layer sends back an incomplete dispatch table with several functions implemented. So the loader will complete the dispatch table that is returned with a function from the previous layer in order to complete the table. So in fact, this table is a shortcut. It points, it skips this layer directly to go into the next layer. And the next layer may also be a shortcut, all the way down to the dispatch of the loader. So we are not paying the functions we are not implementing. So how do we write our CL get device info in this case? What different job has the loader to do? So first, the loader will check if there are layers. And if they are, then forward it to the first layer. Else, you do the regular dispatching, which is checking for the null handle, and call the correct function in the dispatch table. So this piece of code is exactly how it's written now in the loader. Same function, get device info. If there is a first layer, then we use this first layer and we dispatch the call directly. Else, we check if the device is invalid, and we return, we call inside the dispatch table the correct function. So if there are no layers, no active layers, the overhead of the layers is 1 if. So now that we know how the loader works, how should you develop layers and how should you use them? So, as I told you before, a layer is a plugin into the OpenCL library, and the plugin itself is a shared library. There are 2 functions that must be exported, and that allows the layer to be initialized by the loader. A get layer info function to query that the loader indeed implements and what level of the API it implements. And init layer function that is responsible for exchanging the dispatch table. And I will develop a bit on this. Especially the init layer function can refuse to initialize if the loader is not providing it all the function it needs. if you're using an outdated loader, your layer may wish not to initialize because it's missing some function. So if it cannot perform some of its responsibilities, it can refuse to initialize and refuse to load. So it's a negotiation between the loader and the layer. And the loader, if it finds that the layer does not fulfill enough of its API commitments, may refuse to load it. In practice, there is only one API version that is currently implemented. So this is not something that you should see for now. The formal extension is called CL loaded layers, and you can find it on the OpenCL documentation website. And the slides are available on GitHub, and it will be certainly made available afterwards. So you should be able to find this if you wanted to, but I'm going to talk a bit about it. So a CL get layer info API is working pretty similar to the OpenCL function, which are similar, meaning the get info functions. The idea is that you give a parameter name. We have only one which is defined for now, which is CL layer API version. You have the size of the parameter pointer where you want the value to be returned, and you have a pointer where you can query the size of the parameter. So for now, this parameter is CL layer API version type, and it's defined as 100, which is an integer, to say that it's the first API version. It should return CL success on success, and it should return CL invalid value if the name is not one of the supported parameters, or if you specify a pointer value, but the size is too short to store the return value. So this is an example of an implementation of this function for reference. This is the minimal valid implementation as far as I have optimized it. So the idea is that you switch the param name to select the correct case. So in this case, API version, which is the only one supported. If it's not one of the supported one, you return CL invalid value. And if you are querying for the parameter value, you need to check that the size of the pointer given is big enough, as to return invalid value. If it is, then you can return the value of the parameter. And if the user also queries for the size of the return value, then you should return it also. So this is quite a simple function to write. That's one of the functions you need to write if you want to write a layer. The second function is Init Layer. It's not much more complicated, but it does a bit more work. So the idea is that this function is called by the loader. It is passing the loader the number of entries in the dispatch table the loader is giving. And the layer should be returning the number of entries inside its own dispatch table and a pointer to its dispatch table, which can be incomplete. On success, if the layer is happy about what the loader gave it, it should return CL success. And it should return CL invalid value if the loader gave him invalid value, which means any of the pointer is null. And that's more or less all of it. So how can you implement the most simple one? It's quite easy. You need to check that the pointers are not null. Here, I did a simple check to see that the dispatch table is as big as my dispatch table. So the idea is that I have a global variable that says, okay, this is my dispatch table. This is my target, a pointer to my target dispatch table. Okay, and I just check that the number of entries provided by the loader is the same as the size of my dispatch table. So this is the most brutal check, which checks that we are working on dispatch table of the same size. If it's not, this implementation returns invalid value. You could have alternate strategies when you only check that the function you need are actually implemented. This check would be just a bit more complicated to do, but not really. Then I store the dispatch provided to me by the loader. And then I initialize my own dispatch table. I will do that in another function. And I return its address to the loader. And I return the number of entry inside my own dispatch table to the loader. So C initializes structure to null here. So all the pointers inside my dispatch table are 0 unless I initialize it. So here we are going to develop a simple wrapper that I will be using during the demonstration around get platform IDs. So the idea is we want to intercept get platform IDs and display more information about it. Display information about get platform IDs. So get platform IDs takes 3 parameters: the number of entries in the CL platform IDs, the platform pointer, which is a pointer to CL platform IDs. So how many entries can you store here? And the number of platforms which are returned by the driver, by the loader actually. So the idea is we can say, okay, CL get platform IDs has been called with this number of entries, a pointer to the platforms, which is this value, and a number of platforms here. So we print the input parameters. Then we call into the dispatch table that was given to us by the loader to get the next get platform IDs implementation. And we call it. We get the results. And then we print get platform IDs result. And we can also print if the call was a success and the user asked for the number of available platform returned by the ICD loader. We can also print the value that was returned by the function in this pointer. So for the sake of space, I did not put the for loops that would be needed to print the platforms that are returned, but you could also print the platforms that are being returned. And then you finish the line. And then you forward the results by returning it. How do you initialize your dispatch table? You just take the pointer to your wrapper here, and you store it inside of your own dispatch table. And that's all you need to do here. So now that you've written your first layer, which is 70 lines of code, and 8 of those are already macro definitions to avoid warning in the API. So this code is available as is in the layer tutorial GitHub website. So how do you build an OpenCL layer? It's a shared library. So on Linux, it can be pretty simple. You just call GCC minus share to say you want a shared library. You want position independent code. You usually enable all warnings to be certain. I've not made too many bugs. And you give it the OpenCL layers and the path to the headers if you are not sure to have the most recent ones. You may download and install them. And then you output it to a well-named shared library file. So this is one line compiling this layer. I've also developed a simple CMake script that should be portable. At least my GitHub CI says so. To allow it to build it on Windows also, or on Mac. And the idea is that if you're building on Windows, you need a little export file to tell the linker which symbol it should export. So as I told you previously, you need two functions, get layer info and init layer. And that's more or less all. So you can use this CMake script and just replace things which are dependent on this example, which is mainly example layers, example layer.c, example layer.def, and the example layer name here. So if you replace all the example layers by something else, you get your new CMake. So now that we have a layer, how do we load it? How can we use it? The idea is that you have an environment variable for now that you can use. OpenCL layers. It accepts a list of colon or semicolon on Windows separated layers. So you just point the path to the libraries. So you may need to specify a full path if your shared libraries are not in the path, in the LD library path, sorry. The layers are loaded in order and added in front of the layer chain. So the first layer to specify is one which is a deeper in the stack. So it's the last one which will be called. So that's quite important because the others does matter. So let's get an example to understand that with our example layer and a simple layer that only prints the functions when you enter them. Okay. So if we specify the layers and using CL info that I think everybody here has already used. So if you use first our example layer and then a simple print layer, which is provided with the OpenCL ICD loader as a test and example of the layers, this simple print layer. So you can use it if you built the ICD loader. We see a simple print of CL get platform IDs, which is done by the lib print layer, which is called first because it is last in the list. Then we call our example layers, which is with its detailed information. And we see the two-step query here happening, which is, we don't know the size, so we ask the number of platforms. And the ICD loader returns that the number of platforms is 1. And then we do a second query. So CL info says, I have found 1 platform. You do a second query where you say, I have 1 entry in this pointer that points, and I want you to put the platforms inside of it. And I don't care about the number of platforms anymore. And so our example layer here returns only the results, but we see the course between the simple print layer and the example layer, which is done afterwards. So then you have some platform info, which is a simple print layer being called and returning the platform name. For reference, those 2 lines of CN info are what is expected usually, and this is what you get with the layers. If we reversed this, and I will show you during the demonstration, then the orders of the call here would have been reverted. And the CL get platform IDs, which is alone, would have been in between those 2 calls. So I will conclude on the presentation part of the tutorial. So for now, we have a simple experimental layers for OpenCL. Sorry. It provides support for interception and modification of the behavior, because you can change the parameters before forwarding them. You can change the return result of a call if you want to. You can do absolutely whatever you want. You are not constrained. You can use OpenCL call during the layer initialization also. So you can do some quite intricate initialization. We support multiple layers. We have a simple API to implement and configure those layers. And the layers only need to be recompiled between platforms, but they should be portable. You shouldn't need to worry about implementation-specific issues. So, in perspectives, we have an opportunity to develop layers for OpenCL. So the first layers that come to mind are validation layers, akin to Vulkan's validation layer. So the idea is that you should be able to validate that the handles are used correctly using layers. You should be able to validate parameters, even with complex scenarios. You should be able to validate the lifetime of objects, meaning that an object has been released, or you're using it after it's been completely released previously. Did you forget to release it, and so on? And I will demonstrate some of those validation functionalities in example layers during the demonstration. We may want to be developing layers for tracing and debugging. So those have already been implemented as interception layers. There are several of them existing, but we can imagine making them available as real OpenCL layers. We can develop compatibility layers if we can correct the behavior of something, or if we can improve, enrich its behavior to match something else. So an example of this is a layer to be able to bring OCL ICD, which is another ICD loader behavior, and the official Khronos ICD loader closer to one another by using layers to implement the missing functionality in others. So it's not always possible, of course. Some of the functionalities cannot be done this way, but some of them can, in fact. And then, depending on the feedback we get from the user base, we would like to evolve the layer specification. So enrich its API. For now, you can only query for the version, but we may imagine giving names to layer, getting additional information that could be queried from layers so that user can know how to configure them. We may want to add system-wide configuration options. For now, it's only an environment variable, but we could have a directory pointing to layers for system administrators to configure layers that should always be loaded and still provide users with an opportunity to load their own layers. And a more maybe distant opportunity is the possibility for users to, while the program is executing, control layers on a per driver basis, or whatever scheme people would think may be useful. And some may need some additional work on the loader, or maybe on the OpenCL specification. So we will need to see how this unrolls, but those are the opportunities that these layers offer us. So, are there questions on the presentation part of the tutorial? So Evgeny has a question or a comment. I will read it aloud. I don't know if everybody can see it. Would like to say I appreciate this effort a lot. I believe this is the right direction that could bring a lot of benefit in the future. As I understand, this is exactly like layers in Vulkan. I would like to ask, is it possible at the moment to simply use the new loader with layer support instead of the system vendor provided? Here I mean that all the drivers are incompatible with layered loader out of the box. So no. One of the constraints, and maybe I was not clear enough about that, is that it needed to work out of the box for vendor drivers. So vendors didn't have to modify anything. It's a completely loader side implementation of layers. If we wanted to have loader layers that work on a specific device, on a specific driver, then maybe we would need cooperation from the vendors. But for now, the only thing you need to update is the loader drive, the ICD loader. So the libopencl.so or OpenCL DLL on Windows. And on Linux, if you build one, you can use this one by preloading it in your application. So you can build from the official sources the OpenCL loader, and you can use it. So you should be able to use it right out of the box at the cost of updating or building an updated version of the ICD loader. Thank you, Evgeny. Eric has a question on the chat. Do I understand correctly that for each API call, each layer can either not implement anything, API call will be passed to the next layer, do something with the API call, and then forward it to the next layer, do something with the API call, and not forward it to the next layer? And the answer to that question is yes, Eric, this is true. The three scenarios are possible. And for instance, I have a layer that replaces completely the CLget platform IDs to return a sorted version of it that presents as the GPU, the platform that presents GPU first, and that presents also the GPU devices first, I think, in order to mimic what OCL ICD does, because it enables this through an environment variable. So I have a layer that implements this feature. So you specify, okay, I want my platform sorted by device type, and I want the GPU first. And so, in fact, the layer will maintain its own table of platforms that will have queried from the ICD loader, and will return it directly, sorted, instead of the ICD loader doing it. So the layer is a stop point at this point. It returns something and will not forward it later. So if you wanted to intercept those calls, of course, you need to put your layer after in the loading, in the list, in order for it to be before it in the loading chain. So the idea is that the priority of the layers and the order in which you load them is important and will depend on your use cases. The idea is that the lower level work the layer is doing, the lower into the stack it needs to be. Does that answer your question, Eric? You're welcome. Are there any more questions? I think you can raise your hand also if you want to discuss things. So we'll wait. Okay. So another question from Eric. Are the behaviors or layers limited? How do you control for bad interactions between different layers? So there is one pitfall, is that you mustn't call a layer, an OpenCL function through the API directly, else you would create a loop or potentially a loop. There are ways to avoid it, but it could be troublesome. The idea is that a layer more or less should represent a coherent OpenCL API. The fact that you cannot call an earlier layer in the chain should avoid deadlocks. And in practice, it does. But if a layer is badly implemented and sec faults, there is nothing you can do. So the layers has a potentiality to break, like an application bad code would do. And there is nothing you can do about it, I think. So you need to trust the layer you're using. It needs to have been debugged. But in practice, that is something people do a lot. So if you look at OpenCL Intercept layers, it's doing some quite complicated things. I have a THAPI project, which is also implementing a tracer for OpenCL, which maintains a lot of states, and you have synchronization to write inside of it. And in practice, it works quite well. And you can even use the intercept layer and this own interception mechanism also. So it does not allow any more or restrain you any more than previously was when we didn't have any layers. But at least it gives a framework to try to coerce you into using it correctly by forcing you to call through the dispatch table. Yes and no. So Evgeny is saying layers are mostly for debugging and validation. They are rarely used in production. That is true, but you could envision monitoring layers, for instance. You want to know on your HPC platform how are used, what kernels are enqueued, for instance. So you can do a very lightweight layers that will do a small even system to tell you, okay, this application enqueued this kernel, and this application enqueued this kernel, and so on. Compatibility layers also. So there is different kind of layering, and then there is layers I have not thought about, which users will come up with, which I'm very curious to see. Yes, of course. there should not be random layers about it. Evgeny says, I mean that in production, they are either yours or official, and that is right. Meaning official as in official, could be official in the platform's sense, meaning that the system administrator created a layer and deployed it. I'll wait a bit more if there are some additional questions. Okay, Michael is asking, has there been any interest already from NVIDIA or AMD in the Layers API? I believe that at least NVIDIA already uses a customized CD loader implementation on Windows that is enriched with profiling-related code. For example, the Visual Studio profiling extension, at least NVIDIA OpenCL DLL, is significantly larger than the one from AMD. And this seemed like a way towards a truly generic OpenCL DLL on Windows. We sure hope so. I didn't know that NVIDIA was still shipping a modified layer. There are some guys from NVIDIA in the audience, so maybe they want to chime in. I wouldn't want to misrepresent anything. But yes, we are working on having a better loader distribution, a more robust ecosystem to avoid these kind of issues in the future. I hope indeed that the layers are a step in the right direction. And we are taking it, we are hoping to get feedback so that we can bring this kind of support in the most useful ways for the users and the developers of OpenCL. Thank you, Evgeny, for the support. I don't see hand being raised, so I hope I didn't miss anybody. I have the time for one or two more questions, and then we'll take a small break, and I can go through the demonstration. So it's not really a tutorial in the sense that I don't have machines available for you to do the experimentation yourselves, but I will present a bit the tutorial when I start so that you can do it on your own. Okay. No more questions seems to be coming, and even if there are, don't hesitate to ask them, and I will answer them later. So continue shooting at me. I will send the GitHub link at the beginning of the tutorial, or maybe I will do it right now while I take a 5-minute break so that you can look at it if you want to. Welcome back to the second part of the tutorial, the demonstration. So I will be showcasing how you can build a layer environment, OpenCL environment on Linux, and showcase the usage of some layers. So I advise you to work in a separate directory. So I will scratch everything I did previously and start again. So you should be able to copy paste the commands that are on the GitHub page. So let's alias this into a variable for future reference and switch into our folder. So the first thing you need to do is clone the OpenCL headers to have updated headers, because the file you need for the layers to be developed have been added quite recently to the headers. So your system headers may not be up to speed. So let's put the OpenCL headers directory in its own variable. So we just clone it. The second step is to build an OpenCL ICD loader. So let's clone the official OpenCL ICD loader and store this directory in its own variable also. So if we move here, we can one step here is that you can you need a loader to point to the most recent headers. So I will be doing that by doing a symbolic link. You can also add it as a parameter to the CMake process, but linking is usually the easiest way to do it. Then we create a build directory, and we go inside of it, and we build. We configure it using CMake. And we build the loader. It should be straightforward and painless. We will add it to the library path, because if you look here, we have a libopencl.so file. So the idea is that we will make it available for applications to find. That will save us the hassle of specifying that we need to preload the library every time. So now the library is in the path. In all the examples, I will be using a lot of examples. I will be using CLinfo. So the idea is that we are going to build an up-to-date CLinfo also, so that you don't need to have any prerequisite installed on your system, or an audited CLinfo that would complain about the loader. So let's clone CLinfo. Let's save the path of CLinfo into a variable and build CLinfo. So now here we have an updated CLinfo. So we can test it. And I will be using the directory variables in order to be able to use this command everywhere. If I do that, so my driver has a little quirk with my external dongle that I use for the second screen. So it takes a bit of time to initialize. Sorry about that. That's not due to the loader, it's due to the OpenCL driver underneath. Once it's initialized, it's pretty fast. So here we have an OpenCL 3.0 enabled CLinfo with extension versioning supported. And I have a 3.0 OpenCL platform installed, which is Intel's HD graphics platform. So we have a working CLinfo available. So what we can do now is test the layer support, because I told you, if you look inside the OpenCL ICD loader build directory, there is a tests folder where there is a layer folder, and inside of it there is a libprint layer.so file. This is a simple print layer I was talking to you about. So we will use this layer to validate that our OpenCL ICD loader is indeed able to print, to use the layer. So if we look here, you see that I use the OpenCL layers environment variable, and then I'll point it inside this ICD loader here in the build test layer to the libprint layer.so, and I use it with CLinfo. I expect the output of CLinfo to be changed. So I need to carefully choose when I use a command in order to not waste too much time. So here we have the same CLinfo, but as you can see, every time a function call is done, we have a call to we have a print of the relevant OpenCL function. We don't have much more information, we just have the name, but at least we know exactly all of the different functions that were called by CLinfo. So our loader is working, layers are working. Let's do something a bit more interesting. So what we are going to do is to download example layers that are developed and we can use. First, we developed the layer during the tutorial, and I thought it would be nice to use this one first to really connect with the presentation earlier. So we are cloning the OpenCL layers tutorial repository. We will save this in its own variable in order not to look for it too far. And then the example layer is in its own directory. So if you look at it, there is exactly the 3 files we were talking about. So we have the same CMake file that we will use to configure the project. There is the example layers that we developed earlier. And the presentation is generated from this file, so I'm pretty sure it's identical to what's in the presentation. And we have the definition function for the Windows platform. So let's create a build directory, configure it. So in the CMake, I added an option to specify the OpenCL path. So we can use it. Here it is. It points to the OpenCL dir variable we've created earlier. So we've configured our header, and now we'll make it. So now we have a new layer, which is the example layer from the presentation. Let's use it. So let's use it by itself first. So I just made the OpenCL layers variable point to the layer we just built. I could have used a relative path here because it's in the same directory, but I use absolute path because we'll be running those commands here and there. So as you can see, the output of CLinfo is not changed, but for the first call here, where we see the parameters that were passed to CL get platform IDs, and the return value of get platform IDs. The number of platform is returned when it is available. So it is indeed behaving as we were expecting, and as we devised it during the presentation. So now that we have two layers, we can start combining them. So I will be running the command I showed during the talk. So here we put two layers. We put the OpenCL ICD layer, print layer first, and our layer second, which means that in the chain, our layer will be called first, and then the print layer will be called, and then the ICD loader will be called. We'll do the dispatch. So if we look at it, running, sometimes. We have the print layer that does its job of printing the different calls. And we have our layer here. So we can easily see that when we enter the function, we print the arguments. So we are in the example layers. That is called first, because it was last in the list. Then we have the print layer, which is called. And then we exit the function. And we are back in our example layer to get the results that was returned by the previous layer. This layer just forwards the code, so it doesn't change anything. Both layers forward the codes. So we don't have any modification, but we can see how the functions are called, in which order. If we reverse it, here I reversed the orders of the layer. So we have the example layer first and the print layer second, which means that the print layer will be called at the top of the stack, and the example layer would be at the bottom of the stack. We should see a different behavior that would correspond to what was presented during the presentation. Namely, that we first call the get platform the print layer, and then the print layer forward the call to the example layer. So this is all pretty, but that's not very useful layers for now. So we have more example layers available. So let's get back to the root of the tutorial and clone some OpenCL layers that I've developed for this tutorial, and also because some of them might be useful in the future. So let's put this in a variable. And change into here. The layers here behave quite like the loader, meaning that you can specify the headers through CMake or by linking them into the include library. So I will use this strategy here. I will create a build directory. And I will build the example, configure the project, and build the example layers. So it builds 3 layers. The same layer as the one in the loader, the simple print layer, which code I got from the loader and put here. It's just if you already have a loader installed and you don't want to download the loader just to get the layer, it is also inside this repository. You have the OCL compatibility layer, which add support for one of the environment variable of OCL. I wasn't sure I had enough time to use it. It also changes the behavior of the null platform. So if we have time, we may take a look at it. And then I have a small validation layer that checks that you are using OpenCL handles correctly. And that is checking at the exit of the program that you have released all the OpenCL objects. And if not, which are the OpenCL objects that you have not released? So this is the layer we'll be using for the next example. So I'm pointing the layers now to the build object lifetime libcl object lifetime layer, and we are still using clinfo. So the only thing that changed, trust me, is that at the end you have an OpenCL object leaks line, which is returned, and nothing afterwards. There is no warning printed in clinfo. clinfo is managing its object perfectly. So that's an overwhelming example. So I dug around, I took the Wikipedia page and found some list of OpenCL projects. And I looked with my validation layer for leaks. And I found an unlucky project that I will be using for the example. So I also fixed the bug I found and sent it to the author and asked for permission. So I'm not doing it in his back. He knows about the tutorial, and it was a pretty harmless leak. So there's nothing to be ashamed of, but it's better for the demonstration. So the project I found that had issues was Mixbench, which is an OpenCL, which is an heterogeneous programming benchmark, which tests several backends. but it does test OpenCL also. So let's put Mixbench into his own little variable. And we go inside the Mixbench OpenCL subdirectory. So as I told you, I made a pull request on GitHub. So the project is fixed. So we need to check out a commit before it was fixed if we want to observe the behavior. So this is a commit just before I made the pull request. So let's build it in its own directory. The project will see make. There is a little warning during the build because the project does not specify the OpenCL version to use. But that's harmless. I use the system headers in this case. So there are 2.2 headers. I did not use the latest Khronos headers. But anyway, now we have Mixbench. So we can run it first to see what Mixbench is doing. So if we look here, we have two executables, both presented the issue, so I will only be using one. So Mixbench is compiling a lot of different kernels and validating the memory bandwidth and the peak flops it can attain on my laptop's GPU. So it takes quite a bit of time to compile all those kernels. As a matter of fact, I never tried to use a print layer with it. I use another tracer, but we could do for the sheer sake of curiosity. So we have a perfectly fine benchmark. Does it have any leak in it? So let's use our lifetime layer to try and validate the program. For now, we don't print warnings, which mean the handles are not used in an incorrect manner. And the GPU is quite mobilized by the Zoom call, so it's quite slower than usual to do all of its stuff. So here we see that we detected two leaks. The context and a common queue were not released, and at the end of the application, the reference count was 1. So, as I told you, I made a pull request to fix the issue. So if we check out the master branch and rebuild the Mixbench application, and see that both needed to be rebuilt. And we run it with our lifetime layer. The error should have gone away. And we don't see the error anymore. We've used this validation layer in more complex scenarios at the lab, and we found leaks in several projects, some of ours, but some on higher level runtimes, which are not releasing some of their OpenCL objects in some scenarios. So this is a pretty handy tool to have available if you care about memory leaks in an application that could be running for a long time. In this case, it was pretty harmless because anyway, it was at the end of the program. There were 2 handles left, and the program is not going to generate more orphan handles like this. There is no scenario where this could happen. So this was not really an issue, of course. Okay. Are there questions about the demonstration issues? Feel free to ask about it. And if you want clarification, of course, on some of the steps of the demonstration, or if you want to dive into some of the things I presented, feel free to ask for it. I'll say this. Thanks for the tutorial. Thank you, Al. So, in the meantime, while we wait to see if there are questions, we are eagerly, I mean, the OpenCL working group, we are eagerly waiting for feedback. So feel free to come back to us with positive or negative or ideas from how layers could be improved, or other scenarios you would like to be able to realize. We decided to start experimental, meaning that this can still change. I don't expect that the layers we develop will not be able to be used, but we expect to enrich the API in the future based on your feedback. So yes, we are eagerly waiting for your feedback and use cases. And so feel free to come to us with your ideas and remarks. So I don't see questions happening. I will just wait 3 more minutes to see if any question comes up. Feel free to open GitHub issues if you have problems running the tutorial on the platforms I could not test, especially if you have Windows platforms and some of things don't work or could be adapted. Feel free to tell me. If we look a bit at the structure of the GitHub project, the whole tutorial can be executed using this script, which is doing a bit more checking so that you can run it several times. But the whole tutorial is there. Of course, it's only going to work on Unix-like platforms. But if you want to contribute a Windows version, I'll be glad to accept it. Or tell me what I should change inside of it so that it can be adapted to Windows is also something you can do. So feel free to use issues and pull requests on the tutorial. If you look inside the tutorial, you have the presentation. It's a LaTeX presentation, so you can rebuild it, but I put a compiled version inside of it, which should be exactly the slides we've seen today. And I will update it if there are bugs that are found or if need be. You can find the OpenCL layers repository here. It's in the tutorial, but this is there. For now, with object lifetime layer, which is here, which is already a pretty big project. It's 3,000 lines of code. The idea is that it should be foolproof. So if you find a bug inside of it, feel free to open issues and pull requests as usual. And I will do my best to fix any problem you may encounter. The layers themselves are validated through the CI system. So there is a Windows, macOS, and Ubuntu build. So I'm pretty sure they should build, but I've not had the opportunity to try those on Windows. So there may be very well bugs left. Maybe not from the build system point of view, but in the tutorial, I may have missed some things. The layers themselves are platform agnostic, so you shouldn't have an issue with them. Okay, so I don't see any more questions. I will thank you very much, all of you, for attending and for the kind comments and questions you've had during the session. I hope to hear your feedback if you have the opportunity and the need to use our layers. And thanks again. See you next time.